Okay, let's see if you still remember the things that you learned in physics 1. Okay, so let's say you have a thin wire mass that's strong, but it's almost weightless. Okay, so most of the weight is in these two places. Let's say this is 1 pound. Well, let's say this is 3 pounds. And this length is 6 feet. Where is the center of mass located at? Now, question. Here's another way to ask the question. Is it left of the center, or the right of the center? Where's the center of mass?
Right.
It's the right of the center, right? Because this is heavier, right? Okay. How do you actually calculate it? Well, you can use a coordinate system. So let's say x equals to 0 here and x equals to 6 over here. Then what you're doing is you're basically taking the weighted average. You know how to do weighted average, right? So for example, if you took one English class and one math class, but math class is weighted like 4 credits, your English is 3 credits, how do you calculate the GPA? You add the 2 scores, but not directly. You do 3 times English plus 4 times math, and divide by 7, right? 3 plus 4 is 7. That's how you do weighted average, right? You do the exact same thing. You take the weighted average, which is, you take 1 times 0. So the 0 value is multiplied by 1. And 6 value is multiplied by 3. And then you divide it by 1 plus 3, the sum of the weights. So that this is 24 over 4. No, something's not right. 18 over 4, which is 4.5, right? So if you divide this into 4 equal parts, this point where it's 4.5 feet from the left is where the center is. Okay? That's how you do the weighted average. That's how you do the center of mass. Okay. Now, center of mass becomes very important in your engineering courses because in engineering physics, which in this school it's called engineering statics and engineering dynamics, for those 2 classes, which is just extension of physics 1, so you just solve similar problems as physics 1, but you do more harder, complicated configurations, right? And when you do those things, a lot of times you need to know the center of mass of a shape, okay? So in any engineering physics book, if you buy the book and you look at the end, there's an appendix where you have different shapes and the center of mass, okay? So one of the questions that you get to see is, let's say you have a half a disk, okay? So you take a solid disk, which is quite thin, okay? So you take half of it, exactly half of it. And let's say this radius is A. Now in that case, the center of mass should be somewhere over here because of symmetry, right? The question is, of course, it's not 1/2 A, it's closer to the bottom, right? If the density is equal and it's closer to the bottom. So it's less than 1, but what is it? That's the question. Where is it? Now, if you go to the engineering textbook, read the appendix, you can find the answer, but you won't be able to find out why unless you try it yourself using calculus, okay? So that's what I want to show you today. I want you to try this out using calculus. All right, so how do we actually do this? Well, we're going to have a similar idea like that, and the way we're going to do it is, this quantity here is really the average of x. You know this symbol? If you put a bar, that means it's the average of something. So the center of mass, because it's a one-dimensional thing, we are basically calculating the weighted average of x, which you write down by x bar. And x bar is obtained by taking some weighted sum of things and you divide by total size. So in a similar way, if I put this on the coordinate plane so that the equation for this is y equals to square root of a squared minus x squared. You know where this comes from, right? X squared plus y squared equals a squared. That's a circle of radius a. And all I'm doing is I'm moving the x squared to the other side and taking the square root. So I get this top half circle, okay? So that's the equation for that top half circle. And the bottom is y equal to 0. And on this domain, what I'm trying to calculate is, I want to calculate y bar. Okay? And y bar has to do with integral over this domain. I'm putting double integral because and I'm going to call this domain as omega, okay? Over this omega, I'm putting double integral because it's a two-dimensional entity. And what I do is, I am going to multiply y times dA and divide it by 1 times dA. Okay? So here's the thing. If you have constant density, then what is density? Density, we're talking about two-dimensional density here, so it's not mass divided by volume, but it's mass divided by area, right? So that mass is equal to sigma times dA. Maybe I should just use this. So we're going to assume that in this object has a uniform density, which is in a lot of cases when you're working with these type of objects in the machine shop, it's likely that it's a constant density, right? Uniform density. Okay. So if you have that, then the weight of any point, any small region will have small mass and small area, and the weight, which is dm, can be calculated by the sigma times dA. I don't know the value of sigma, but that's okay. You'll see that it cancels. And you kind of know that sigma doesn't matter, right? If you increase the density of this, that's not going to change the location of the center of mass. Does that intuition make sense? Mm-hmm. If you're really trying to make sense out of what I'm explaining here, that should just make sense. That should be obvious, okay? But anyways, this is the mass. So what I'm doing is I'm doing weighted average. So I'm multiplying y by the weight, which is dm, right? Which is sigma times dA, and dividing by total mass, total weight, which is sigma times dA itself. But look, if sigma is a constant, that can be brought outside the integral, and you end up with y dA divided by just dA. Okay. So let's try to calculate this. First, just the top. What is the integral over this domain y dA? Well, we can paint this region going up, right? So we can go up, and what that's doing is you're starting from 0 and you're ending at square root of a squared minus x squared, because that's the top boundary, right? And then what about the x value? X goes from? If you integrate this region, what do you get? It gets populated on the x-axis, right? So negative a to positive a. And y Now, is it dx dy or dy dx? Dy dx because you're painting upwards, right? So it's dy dx. So that you get negative a to a, 1/2 y squared is the integral by y dy. If you integrate y by y, you get 1/2 y squared, and you're plugging in square root of a squared minus x squared, and 0 dy, and then still dx. And that gives you, when you plug this in here, the square is going to cancel out the square root, so that you end up with 1/2 integral from negative a to a of a squared minus x squared dx. And then we're going to use that trick of, these are both even functions, so we're going to take half the interval, and 1/2 will be erased because you have to double this area to get this area, this much. So the 1/2 vanishes because I changed the interval to half of the original one. And its integral will be a squared times x minus 1/3 a x cubed. And then you're plugging in a and 0. So you get a cubed minus 1/3 a cubed, which is 2/3a cubed. Okay, now what about the area of this thing? What's the area of this half circle? What's the area for the circle, full circle? What's the formula for the area of a full circle? Pi r squared. Here, radius is a, so the full circle is pi a squared. Therefore, half of pi a squared. So this is now going to be whatever we got here, 2/3a cubed divided by 1/2 pi a squared. Now, if you simplify this, you get 4/3 pi a. That's the answer. Okay. Now, here's the homework. When you go home, look for the center of a semicircle. Okay. Yeah. You can look it up now if you want to. Yeah. Then you'll likely see some PDF file from engineering statics course or some hard physics course. Yeah. And you're going to see exactly this.